Great. All right, so the first thing I want to do is a demo that I basically stole from someone named Dan Garcia, who gave a talk at UBC a couple of years ago called The Beauty and Joy of Computing. I ported his stuff into Python, but basically we're just going to draw some pictures, and you can ignore all of this plotting code. But what we really want to, the line of code that you really care about is this part. So I have a list of shapes, square, hexagon, and star. And this function here is called v. And what v does is it uses np.random.choice, which you've used before, on shapes. So it's randomly picking one of these three shapes, and then it's drawing it to the left. And then it's randomly picking one of these shapes again, and it's drawing it to the right. So each shape is picked randomly, and then they're being drawn when I call this v function, and I get something like this. So here I picked a square and a star, and those were just picked randomly. So if I run it again, this time I got 2 stars. This time I got a hexagon and a star, 2 squares, etc. So again, what this function does is it takes a shape from the list, draws a branch of the tree to the left, plots that shape, picks another shape at random, draws a branch of the tree to the right, plots that shape. So the question is, what happens if I add v itself to the list of shapes? So again, v is the name of this function. So now I could pick, and I'm going to add it twice so it's actually slightly more likely that it gets chosen. So with 2/5 probability, 40% it's going to pick v, and with 60% it's going to pick one of those other 3. And v is actually this function. So square, hexagon, and star are also functions. So what do you think it's going to draw when I run this code? Any guesses? Tom?
Does it have a chance of drawing another branch on top of it?
Exactly. It has a chance of drawing another branch on top of it. So let's run the code. OK, well, that time, actually, the same thing as before happened. So what we're seeing here is that it just randomly chose star and randomly chose hexagon. So it doesn't have to pick v. V is just in the list of things that it's picking randomly. So let me run it again. Whew. Wow, so what happened here? Well, what happened here is that the left branch picked star, and the right branch picked v. And what does v do? Well, it picks 2 things, a left branch and a right branch. As it so happens, in this case, both of them picked v again. This v over here picked hexagon and star, so that one kind of terminated. But this one over here actually picked v again twice, and it just keeps going, and it's kind of set up to make the demo look nice, having v in there 40% of the time, that sometimes it calls one of those shapes which just terminates the tree. That's like a leaf of the tree, a square, hexagon, or a star. But sometimes it's picking from this list v, which is that entire function again. The function v is calling itself. The function v is calling the function v. And what does that do? Well, it randomly picks those things, and it might pick v again, or it might not. And that idea of calling yourself is called recursion. And we'll actually talk about trees specifically on Thursday. But any questions about this drawing? Furkan?
Yeah, what change did you do to have things like this?
What change did I make? So to have the branches. The change I make is that when I first started showing this to you, the list of possible shapes only had square, hexagon, and star. And those are 3 Python functions that just draw a shape, and they don't do anything fancy. And so there, I could call this millions of times, and it would just pick 2 of those shapes. But once I added v to the list, and I just added it twice to make it more likely so the trees would look nice, so you could try adding it once yourself. Once I added v itself to the list, I got all sorts of things. And sometimes it's not a big tree, it's random, right? So this time it just picked v on the left and hex on the right, and then the v on the left just picked star and hex. Yeah, you never know what you're going to get. But sometimes you'll get big trees.
Jarvis?
Yeah.
Yeah. Which one finishes first?
Which one finishes first? Yeah, so we'll be talking about that, but what happens is that Python basically does the left branch. It picks a shape, and then here it calls that shape function. So it's basically going all the way left. So it's really going, it's really drawing this square, and then going back here, this V, this star, back here, this square, and so on. Tom?
Is there a chance it could end up in like an infinite loop by mistake?
Is there a chance it could end up in an infinite loop? In general with recursion, yes, and we'll see that later today. Just like a while loop that might never end. But this one, it's kind of probabilistically it will eventually terminate because it's going to pick one of those three enough times. I mean, if I just removed these all, yeah, then it would just be an infinite loop. Any other questions? Okay, so that's not like, that's the big picture, cool looking tree thing. But now we're just going to go excruciatingly step by step to really try to build this from the ground up. So yeah, it might get boring, but I just tried to take the smallest leaps of logic possible to try to keep it together. And even doing this, it's still a very difficult concept to grasp in programming. Okay, so here's the friendliest function I could think of. Def h takes no arguments, just returns 0. So we've seen functions before. That's fine. We can call the function. It returns 0. That's fine. So now we're going to do something that we did a little bit of in the programming course, which is one function calling another function. That's completely allowed. So now I'm defining g. Again, it takes no arguments, and it just returns h plus 1. So what's g going to return? 1. Yeah, so what's going to happen first is this h call is going to happen first. That's going to return 0. Then it's going to do 0 plus 1, which is 1. And so when I call g, it's going to return 1. And there's no randomness here. There's no arguments here. So that's just going to be the case every time. Not very useful function so far. OK, so this is what we talked about. G is calling h, which returns 0, etc. So now let's have a function f that calls g. OK, we can define this function. So here's what's going to happen. F needs to compute g plus 1. And there's two ways of thinking about this, which are both useful. One is, well, we already know that g returns 1. So g is going to return 1. 1 plus 1 is 2. We're done. The other way of thinking about it is, well, what does g do? G actually calls h plus 1. And h actually returns 0, so it's going to be 0 plus 1 plus 1. And that's going to give us the same answer of 2. So, I mean, there is actually an order of things that are going to happen. F is going to call g first. G is going to call h first, and so on. But conceptually, you can think about it either way. Either we already know what g is going to do, so let's not bother thinking about it too much, or kind of taking it all the way to the bottom, which is h returning 0. Questions or comments about this? Okay. Step 2. Functions with inputs. So those functions didn't have arguments. Now let's allow our functions to have arguments. So h of n, it just prints, you called h with argument n. That's the beginning of the function. Maybe it does some stuff in the middle, maybe not. And then it prints ending h with argument n. And I can call this with 3 and 2, etc. So at least we're actually using function arguments this time. In that sense, stepping up the complexity a little bit. OK. So how about this function, g? So g of n prints, you call g with argument n, and then it calls h of n minus 1. And then it ends g. So what's going to happen here when I call g of 1? Now we can see these order of things happening, these functions within functions. So So we're going to first print that we started G, then we step inside of H. And then we start H, then we end H, now we're back to G, and now we're ending G, and so we're printing this. Any questions? If at any point in the next while you're seeing some output and you don't understand why you're getting that output from that code, please raise your hand. OK, so we can call G of 2. And it's always calling H of n minus 1. So G of 2 calls H with 1. G of 3 calls H with 2, etc. OK, now we're going to add F. So F calls G of n minus 1. And with these print statements letting us know that we're starting and stopping the function. So by now, there's kind of a pattern that's emerged. When I call f of 5, it starts f with n equals 5. Now we're inside of G with n equals 4. And again, those variables are both named n, but they are not the same n, because inside of the f universe, n is 5, and inside of the G universe, n is 4. And then G calls H with n minus 1 again. And this is one place where recursion really trips people up, is it's kind of like the n of G is the n of f minus 1. But they're both called n. That's part of where it gets confusing. I could have called them different names, but I don't want to because I'm going somewhere with this. So each function has its own variables. They're named the same thing, but they're in different universes. They're taking these different values. And then the n inside of the H universe is 3. So we can't just say n is something exactly. It depends which function we're inside of. Questions about that? Yeah, what's your name again?
Mohammed.
Mohammed.
How could you define, you said you could define something else other than n? Like, how would you do it?
Yeah, the question was, how could you define something else other than n? Well, all I was saying is I could call this A, and I could run the code and I would get the exact same results. A minus 1. And I would get the exact same results. But
They still have the same name, all the functions, A.
well, the functions here are named f, g, and h. A is an integer here. So A is not a function. I'm just saying I want to name it n inside all 3 functions. I named it n up here. I named it n up here because I'm going somewhere with this. But that introduces a potentially confusing fact that inside of the different functions, the integer n actually has different values. Tom?
Why does this not continue on into the negatives?
Why does this not continue on to the negatives? Because,
That is something?
well, first of all, I could just call like f of 1, and then it would, because it's just going down by 1 every time. So I could make it go into the negatives. But the point is that f is calling g, g is calling h, but h is not calling anything. It's just printing. So I'm only going 3 steps in.
I understand. Thank you.
Any other questions? OK, so I could call f of 10. It goes 10, 9, 8, 8, 9, 10. And maybe I'm kind of regretting, instead of with argument, maybe I should have said with n equals, just to hammer home the idea that each function thinks that thing is called n, but they're taking on different values. OK, so this is just an optional note, but there's something called a call stack in the way programming languages work, that basically you're inside of f, and then you step inside of G, but you need to remember that you're inside of F. And then you step inside of H, but you need to remember you're inside of G, so that when you're done with H, you can keep going where you were in G. And then when you're done that, you can keep going where you were in F. So in the back end here, there's this thing called the function call stack. It's basically just stacking up. I'm inside of this function, inside of that function, inside of that function, inside of that function. And you're kind of going deeper and deeper into functions within functions, which is where we're really going here with this recursion stuff in a minute. So if you're interested, you can read about that. Okay, step 3, functions with inputs and outputs. So here's what we're doing now. Now I have h of n. This is a very silly function that just returns 0 like before, like the first time. So now h is taking in a variable n, and it's returning a value 0. Before we were just doing one or the other. So no matter what n you call here, h is just going to return 0 because value equals 0 is hard-coded here into h. So it's not even looking at n. It's just printing out, here I am with n, and then I'm setting value to 0 and saying I'm ending with 0, and that's it. Okay, so not a very useful function, but we're going to go somewhere with this. Now look at g. Here's what g does. G says what it's starting with. So it's starting with argument n. And then it calls h of n minus 1, which we were doing before. But then it's also getting what h returns, which we weren't doing before, and adding 1 to it, and then saying what it returns. So, and this is where we're having to think of a bunch of things at once when we talk about these types of things. We have to think of all the data going in, chaining from one function to the next and next and next and next. And then we also have to think about all the data coming back from those functions because we're returning things typically. And that's where it starts to mess with our minds because there's just a lot of things to keep track of. So here's what happens when I call g of 10. It starts g with 10. It does what we saw last time. It passes in n minus 1 to h. So inside of h, n is 9, so it prints that out. Then h returns 0, and it says h is ending with the value of 0. It passes that value of 0 into g and adds 1 to it. And so when g ends, the value is 1, and this 1 here at the bottom is showing that g is actually returning that 1. Still not useful for anything, these functions, but just for talking about recursion. Any questions about this? My goal here is that you could look at the code for f, look at the code for g, and predict this behavior of calling g of 10, that this is what would have got printed out, and this is what would have got returned. And it's really a matter of just methodically, step by step, okay, here I am in G, I'm doing this. Now here I am in H, I'm doing this. And now I'm back to G. And it's just a lot of things to keep straight in our minds. But at the end of the day, the programming language is going to follow the rules. So any questions? Yes?
And how did we end up with ending h with value 0?
How did we end up with ending h with value 0? That's just because h is weird and always ends with value 0 no matter what. So h just... Go ahead.
That's in the function g, right?
Well, I called the function g, and g prints stuff out, but g calls the function h, and h also prints stuff out. And so those things all get printed out. And from the order of things getting printed out, the reason why I'm printing things out is so you can watch which function we're in as it goes along. So you can see we started in G, then we stepped into H, did all our stuff there, stepped back out into G. Tom?
So as a way of thinking about this is, and within these functions, n is like kind of like a global variable within the function? Or like a function variable? I don't know how to describe it.
Yeah, you could call it a local variable, I guess. I mean, within the function, n is just for use within the function. Yeah, so it's
you're jumping from functions to functions, just like a local. I know it's not global, but like, just because everything's linked together.
Well, I would think of it as a coincidence that they're called n in both cases, and basically an irrelevant coincidence. And the only thing that matters, because for any function, I could, as I did before, I could change this name as long as I change it everywhere inside of G. Because all that really matters is it's saying the thing here needs to be the argument that was passed in. And the thing here needs to be the argument that was passed in. And whether you call that N or A or Tom or whatever, it makes no difference. So it's just kind of saying those three things are the same thing. And so we're calling them all N just to show that they're the same thing. But then inside of H, those three things are the same thing but have nothing to do with these three things. Great questions. Any other questions? Okay, so let's look at the order of the print statements. We already talked about this. We start G, then we start H, then we end H, then we end G. And we can see that from the print statements. Okay, so here's F. F takes an argument N, prints a thing out, calls G with N minus 1, gets a result, adds 1 to it, and then ends. So now we're at our depth 3, F is calling G is calling H, and they're all taking stuff in, and they're all returning stuff out. And so if I call F of some value like 11, then here's what happens. F starts with 11. It prints something out first. Then it steps into G. Inside of G, the argument is 10, because I'm passing in G of N minus 1. What does G do? It immediately prints something out. We can see that on the screen. Then it steps into H. H immediately prints something out, which is 9. And then H does this weird thing, which just sets the value to 0 no matter what. Prints that, passes that 0 back out to G. And G says, oh, I had to take that value and add 1 to it. So it got 0 plus 1 is 1. Prints ending G with value 1. And then G is done. G returns back to H. And H says, I have to take whatever I got, which was 1, and add 1 to it. So now F is holding on to 2, and so F both prints and returns 2. Questions or comments? Tani.
Both H and G have return value, right? It's not just F.
Yes, correct.
So why isn't 0 and 1 printing separately?
Because what IPython does is, the question was why is only 2 being shown up here, not the 0 and 1? This is an IPython thing, which is basically means a Jupyter thing, which is that if you just call a line of code in Jupyter, it just prints out whatever the result is of that thing.
At the end only?
Yeah. Well, but that's the thing. I mean, yeah, that is the result. The line of code F11 only has one result, which is 2. Those other things just happened in the middle. It is irrelevant that they were functions calling functions. They could have just all been stuff happening in the same function. At the end of the day, F of 11 only has one result, which is 2.
But they do have a return. Like if this was running 9 Jupyter, this was running it.
If this was running 9 in Jupyter, it would just print nothing. And you would have to
Right.
you would have to go
I see.
print
Right, because-
F of 11, and then you would get this 2.
Okay, I got it. Thank you.
And by the way, you can do that behavior in Jupyter by just putting a semicolon at the end. So that just says, don't print out the thing into your screen. Yeah, Braden?
Yeah. So the other return calls in the other functions aren't returned? Only the one that you're calling?
Well, so F of 11 returns 2. End of story. It just so happens that to get to that value of 2, F happened to call G, and G happened to call H, and they were passing information back and forth to each other. But at the end of the day, F is just a function. It has inputs and outputs. The input was 11, the output was 2. The fact that it got that result of 2 by calling other functions and they were returning things doesn't change the fact that its result is just 2.
Okay.
Yeah, so I don't know if this would be more or less helpful going to Tani's and Braden's question, but you could also do this. Just say I'm getting f of 11, storing it in a variable, and then I'm just printing out that variable. I'm not printing out anything else. Okay. So now let's remove some of the print statements. We're getting close to the punchline here, so hang on. Let's remove some of the print statements. So this is all the same code. I just removed the print statements at the end. So when I call f of 11, it just has the starting parts. But that's the exact same code as before. It's still returning 2 the same way. It's still printing the same starting things. And now we need to make it a bit more interesting because n is not being used. So right now, n is only being used to print stuff out. If I give it a different n, it's going to print different stuff out, 1,000, 999, 998. But I'm not actually using n in the thing it returns is just always going to be 2. F returns 2, end of story, no matter what n I give it. If I give it different n's, it'll print different things. But at the end of the day, f is a function that returns 2 so far. Because it calls g, which returns 1, and g returns 1 because it calls h, which returns 0. Okay. So how about this code? F has a special case in it now. That if you pass in 0 to f, it's going to return 0. So that's a different behavior from what we had before. Otherwise, it's the same behavior as we had before. So we're just adding a special case using an if statement. If n is 0, suddenly alarm bells, this is different. We're just going to return 0 and not do anything. Otherwise, just the stuff we've been talking about for the last few minutes. Call g of n minus 1, add 1 to it. And I'm going to implement the same thing in g. If n is 0, call h of n minus 1 and add 1 to it. And what I'm going to do now, this is the biggest change, a major departure from what we had before. H is also going to have that special condition if n is 0, return 0. But before, h always returns 0. H was this ridiculous function until now that, sure, maybe it printed some stuff, but at the end of the day, it always returned 0. It was not interesting. But now what I have is that h is going to call some other function. H is going to call some other function called I, passing in n minus 1. And now imagine I defined an I that was... Notice that these functions are all exact copies of each other, except they have different names, and they call the next one. So f calls g, g calls h. You could imagine h calling I calling j. And you could I could spend hours writing infinitely many of these functions, but it would be kind of boring. But let's reason through what actually happens here. Yeah. Okay, the question is, what does f output? Well, if I call f of 0, it just immediately returns 0, because that's the first thing in f. If n equals 0, returns 0, done. So this first line that I'll reveal at the bottom, we can understand. F of 0 is 0 because that's just the if statement at the very top of n. But what happens if we call f of 1 now? Now this is where it gets interesting. If we call f of 1, this is not true. This if statement does not trigger. So it says, OK, I'm going to go into this else, and I'm going to call g of 0. Because that's what we've been doing all along. We've been calling the next function, but making n smaller by 1. OK, but what is g of 0 going to do? It's just going to return 0. And so it's going to get this 0 here and add 1 to it. And so f of 1 is going to return 1. And I can run the code, too. I just put it in the table. Any questions about why f of 0 returns 0 and f of 1 returns 1? Okay, what happens if we call f of 2? Well, if we call f of 2, then n is not 0, because we just said n is 2. So it's going to call g of 1. And now we're inside of g, and n is 1. And n is not 0. So we don't do the special thing here either. So now we actually call h of 0. And now we're in here. We're inside of h, and n is 0. And now we trigger the special thing. So we actually never call I. Because by the time we got down to h, n was already 0. And so we just said return 0. And now g got the result it wants, 0. It takes 0 plus 1. Great, it has 1. Returns that back up to f. F got the result it wants, 1. It takes 1 plus 1. That equals 2. It returns 2. And f of 2 is 2. But now what if I call f of 3? Well, if I call f of 3, then inside of f, n is 3. Inside of g, n is 2. Inside of h, n is 1. And it is going to try to call I, and I doesn't exist because I never bothered to write that code, so it was just going to throw an error. Yeah. So let me run these for you. Any questions about the behavior we just saw when calling f with n equals 0, 1, 2, and 3? Notice that as I was increasing n, I was allowing it to go deeper by one function into this chain of functions that I've written. By the time I got to 3, it was trying to go 3 deep into I, and since I just happened to never write the code for I, it just threw an error. But other than that, f of n was actually just returning n because I happen to be adding 1 every time, and so however deep I go, I'm adding 1 every time, and I just get back that same number. Questions? Okay. Now it's time for the magic to happen. Here's the thing. All those functions above were exactly the same. They had different names, but they were exactly the same. What did they do? They checked if n is 0. If n was 0, they returned 0. Otherwise, they call a function identical to themselves with argument n minus 1, and then they add 1 to the result. If I had sat there for infinitely amount of time and written function I, j, k, all the way, and I just written infinitely many functions like that, and I defined them all in Python, then if it really went on forever, then all the functions are identical because, I mean, it doesn't really matter how long the chain is. So really what these functions do, again, they check if n is 0, if not, return 0. If so, return 0. If not, they call a function just like themselves. Just like themselves in every way, except with a different name. But the name's irrelevant. The name is just for human purposes, so we can refer to things. And usually, if you give two functions different names, they're going to be different, like, you know, plus and minus or whatever. I mean, why would those do the same thing? It doesn't make any sense. But here, we gave functions different names that do the same thing. And so then the question is, why am I bothering to give them different names? They all do the same thing. So why do this when you can just do this? This is what we were just dealing with. This is a function in Python that takes an argument n. And if the parameter is 0, it just returns 0. And if not, it returns a function identical to itself with n minus 1 as the argument, and then adds 1 to it. But now we just didn't bother writing f, g, h, i, j, whatever. We just said, why should we? If the behavior we want is to call a function identical to itself, let's just call it self. What's the difference? And this does have all the same behaviors. F of 1 is 1, f of 2 is 2, f of 3 is 3, but I can call f of 5 or f of 100, and it's going to work now. It's not going to throw an error, because I don't have that problem of I being undefined, because it's just calling f over and over again. But, and here's the tricky part, before we said the n inside of f was different from the n inside of g, and now is the truly evil part of this. I don't know if evil is the right word, but the tricky part of this is now the n inside of the first f is different than the n inside of the second f. Because f is calling itself, and last time we gave that a different name, and we were more comfortable saying, oh, it was the n from f and the n from g, but now we have the n from the outer f is, say, 100, but then it's calling f of 99. In that universe, n is 99. And then it's calling f of 98, and in that universe, n is 98. And we can put the print statements back in and see that happening. That in the first f, n is 2, and then in the next f, n is 1, and then the next f, n is 0, and so on. Any, yeah?
What's the difference between the two different ways of doing it if you put a negative number?
So going back to Tom's earlier question about an infinite loop, if I put in a negative number here, I'm going to get an infinite loop because it is going to call f of -1, f of -2, f of -3, f of -4, and it's never going to trigger that stopping condition, which we call the base case, which is n equals 0 in this case, and so it's just going to blow up my Python.
So we just need to make sure that the base case is always somewhere later. Which
Yes, it's kind of like a while loop. You need to make sure everything's okay, otherwise you could get an infinite loop. So let me show this again. Yeah, so it's just incidental that all the functions have the same name f. You may want to think of them as separate. They have separate variables. And the fact that they're all named f is just a matter of convenience, so we didn't have to write an infinite amount of code. Yeah, Sam.
Could you explain how how it prints out everything?
Yes. So the question is, how does it print this stuff out? So we started by calling f of 2. So it immediately prints starting f with argument 2. Then it checks if n is equal to 0. That's false. So it goes to the else case. The else case tries to call f of 1. Because in order to compute value, it needs f of 1 plus 1. So the next thing Python starts doing is says, let me go in and see what f of 1 is. Now, we're in f of 1. Now, go back to the top again. Now we're inside of f of 1. The first thing that happens is that it prints starting f with argument 1. It checks if n is 0. It's not. So it tries to compute value and says, I need f of 0. Now I'm inside of f of 0. Is n equals 0? Yes. So it prints out something slightly different. And it actually returns 0 instead of calling another function. Because in that part of the if up here, there are no more function calls. There's just a return. So now we are done with f of 0, and we step back into f of 1, just like we were stepping from f to g to h, and then back to g and back to f again before. We're stepping from f of 2 to f of 1 to f of 0, and then we're back in f of 1. And then f of 1 says, oh, I got this value from f of 0. It was 0. Great. Let me add 1 to it. Now I have 1. Great. Now I can print this thing out and return. And that's what this print is. And now you're back in f of 2. And f of 2 says, oh, great. This thing finished. Now I know that f of 1 was equal to 1, so I can just add 1 to it, get 2, print, return, and now I've actually gotten to a return statement from the original function that I called, so now I'm just done. Other questions? Furkan.
Is there any way to, just visualize, is it better to visualize these recursive functions instead of just running inside your head?
Yeah, we'll be drawing some pictures later today. But yeah, you could visualize this. You could at the very least say, f of 2 calls f of 1 calls f of 0, and then you go back up to f of 1, and you could do something like that. And it is helpful. Yeah, Tejas.
Is the time complexity linear in this?
Yes, in this case, the time complexity is linear because for a given n, you just have to call n functions. So does this look familiar? It's the same call stuff except they're all named down. The n equals 0 part is called the base case. We talked about that. That's basically the case when you stop calling yourself, stop recursing, and just say, I'm done. Now I'm just going to return some value like 0. And this part is the recursion, calling yourself. OK, we're a bit behind schedule, so let's take our break now and return at 10:17. The thing I wanted to do is revisit binary search. So in lecture 2, do I dare click this link? Yeah. Anyway, in lecture 2, we talked about binary search, which was, again, we had like a sorted list and we were searching for something, so we looked in the middle and then one half, then the other half. Sorry, not then the other half. If the thing we were looking for was smaller than the middle element, we only looked at the left half because we didn't need to look at the rest. So, and the code, you can go back to lecture 2, look at the code. It was a bit of a mess, had the high, the low, the rounding, the loop. The code was a bit hard to read for binary search. So look at how beautiful the code is for binary search with recursion. So same docstring as before. I just copied the docstring from lecture 2, which was last class. So I have the list. I'm calling it data. I have the key that I'm searching for. So here's how it's going to work with recursion. If the list is a length 1 list, meaning if there's only one thing in the list, then, well, just check if the thing I'm looking for is that thing. What else can I do, right? And if return, so data 0 just gets that one element, and then I just check if it's equal to the key. If it is equal, that evaluates to the Boolean true, and I return true. If it's false, that evaluates to the Boolean false, and I return false. So that makes sense. If I have a list with only one thing in it, and I need to search in it, I'm just going to say, is that the thing I'm looking for, yes or no, period. That's the base case. Now here's the recursive part. First, I get the midpoint of the list. So if the list is 10 elements long, then element 5 is the midpoint, etc. And just to remind you, I'm using that double slash, so it rounds to an integer. So if the list is 9 things, then the midpoint will be 4, just because I need it to be a valid index into the list. And then I have this. If the thing I'm looking for is less than the element sitting in the middle, so here, let's say I'm searching through this, let's say I'm doing this in the docstring and I'm searching for 3. So I look at the element in the middle, that's 35. If 3 is less than 35, remember, then I'm only just going to look at the left half because 3 is less than 35. It can't be to the right of 35 because the list is sorted. That's the whole point of this. So then, if key is less than that middle element, if 3 is less than 35, then I'll just do binary search on that smaller part of the list. On the list from the beginning to the midpoint, searching for the same key. And if the thing is not less than, if I was searching for 100 and the middle element was 35, then I'm just going to do binary search on the right half of the list. And it's just going to keep chopping and chopping the list in half. And it's eventually going to trigger that base case where there's only one thing in it. So this code is effectively the same as the code I showed you last class, but it's so elegant. It's so easy to read, at least when you're in the hang of, maybe not right now, if this is your first day seeing recursion, but it kind of expresses, like the translation from words to me describing how it works to code is almost like direct. It's literally just saying, find the thing in the middle. If it's less, just search in the left half of the list, and otherwise search in the right half of the list. And there's this thing where you kind of have to trust that when you're calling itself, it's going to work and do what it's supposed to do. Again, you kind of have to think it through that, yeah, eventually this is going to reach a list of length 1, because either it's like starting as a, maybe it'll be a list of length 4 and then a list of length 2 and a list of length 1, or if it gets to a list of length 3, just because of that truncation, it'll split it 1 and 2, and it'll all work itself out. So my point of showing this is just to say, sometimes code can be very nice when you write things recursively. Alistair.
Would you always wait till the base case to check something for this specifically and generally recursion, or could you, after you get mid, check like is mid the key? Or is it better practice to wait?
The question was, why are you only checking when you get to the end? Why not check if mid is the key? So I guess you could do that, but it wouldn't really matter. Like, I guess it would probably just be faster in some cases and slower in the other cases, but pretty much the same thing at the end of the day. Yeah, in fact, I mean, that would probably work in the sense that if you had a list of length 1, then the midpoint would be, so it would probably work to do something like this. If data mid equals key, I don't know, something, you could probably make it work like that too. Yeah. Okay, so I'll just run the tests and show that they pass. Any other questions about this code? Yeah, Sam.
So right when you have mid, like you have the if len, and then you have mid is equal to
Yes.
that condition there.
Yes.
Why didn't we put like a elif or an else after the mid?
Oh, yeah. So the question is, why didn't we put an elif or an else? That's purely a stylistic choice. You could do this. And you might think that's more readable, but the truth is they're identical code because since the if part has a return in it, if you get into the if, you're never going past that anyway. And if you're not into the if, then you're in the rest of the stuff. So when you do if some condition return, then putting an else there or not is just a stylistic question. Tom?
So recursion's only useful when you have like a finite, you can make it a finite amount of cases?
Recursion is only useful when you can make it a finite amount of cases. I mean, I guess that's true about most things we do with programming. Like if there's an infinite amount of stuff to do, we couldn't do it. So yes, but that's not like a big restriction. Any other questions? Okay, so you might need to look at this at home and digest this and go back and look at the code from lecture 2 and compare them. But I just wanted to highlight how this function looks when written recursively. Okay, yeah, oh, so the phone book thing, right? So for those of you who watched the phone book video, this is really the ripping of the phone book here. Like it's very clear. It's like I'm just taking the stuff up to mid, I'm ripping it at mid, and I'm just throwing away all the rest, and I'm only taking the stuff up to mid and continuing my search. So I think that's kind of nice. This is like, yeah, okay. Okay, we have to keep going. So multiple recursive calls. Okay, so consider the code below. If n is 1 or n is 2, it returns 1. Otherwise, it returns f of n minus 1 plus f of n minus 2. So what that means is if we call f of 3 here, then it actually needs to compute f of 2 and f of 1, because it has to compute f of n minus 1 and f of n minus 2. So that means just by calling f of 3, f is actually calling itself twice. It's calling f of 2 and f of 1. And as it happens, both of those are going to trigger the base case. Both of those are going to return 1, and it's going to say 1 plus 1 equals 2. But when I call f of 4, things are going to get substantially messier, and so we want to start drawing things out. So if I call f of 4 here, then it's going to say, well, that is going to be f of 3 plus f of 2. F of 4 is going to call itself twice. And f of 2 is just going to immediately return and say, well, f of 2 equals 1, because that's part of the base case. If n equals 2, return 1. But f of 3 is not done. It's not triggering the base case. So this is actually calling f twice again, f of 2 plus f of 1. And both of these are triggering the base case and getting 2. And so now it's bringing this 2 back up here and saying 2 plus 1, and bringing this 3 back up here. So we can first verify that we actually get 3. And then we can do this print thing. We can insert this print statement at the start of the function just to see what's being called. So f of 4 is calling f of 3. This is what's happening. And f of 3 is actually calling f of 2 and f of 1 next. And then this is happening at the end. So once the function is calling itself multiple times, we start to get these more complex kind of structures of the functions within functions within functions than just a linear chain like we had before. F of 5 calls f of 4, calls f of 3, calls f of 2. Now we're in crazier territory. And so it helps to draw these types of things. And I think Thursday's lecture is relevant to this as well. But it starts to be a lot to keep track of. Are there questions about this? Yeah, Annie.
So a lot of this seems kind of like how you would do math with stuff in the brackets first and so on and so forth. Why is it that they didn't do that here? Like, why do we always write it out separately like this rather than doing it like a math formula? Is it just for stylistic?
So how would you write it as a math formula?
Wondering like why didn't they make the script so that you could, you know, just nest function within a function within a function?
But what would that look like if you were writing the math?
I guess like I don't know. I'm not thinking of an example, but just like a function and then f bracket, kind of nesting it almost.
Well, you can do that, and that's a bit different from this. I thought I had some of that. So, you could make a function that just adds 1, and you can in Python do this. And it's going to add 1 4 times and give me 9. But that's not actually recursion. That's just, well, this happens first. It adds 1 to 5. It gets 6. Then the next thing happens. So add 1 is not a recursive function. Is that what you meant by the math?
Yeah, I think I have a question.
No, not at all. It's just you can compose functions like this in Python. You could also do f of g of 1 or whatever in Python. But that's composing functions rather than recursive functions. Other questions about this function that calls itself twice? Jerome?
Would we generally want to avoid that because it makes, I guess it might be kind of a lot of work going on behind the scenes?
That's right. So the question is, would we want to avoid this? Because that would be a lot of work. So in this case, we would want to avoid this. So this is actually, some of you may recognize that this is computing the Fibonacci numbers. But it's something that you could compute in a much more efficient way than this. And this is not an example of when it is a good idea to use recursion. It's just an example of a function that calls itself twice. However, there are cases where it is a good idea to use recursion, and we're going to see that next lecture and in the lab this week when we start building these tree structures, because this is starting to look like a tree. And the thing at the very beginning, well, it was literally a tree that I was drawing, but trees can actually be useful to us, and this can help us express them in a way that would be not very reasonable without recursion. So we'll be seeing more of that soon. Okay. Right. I also wanted to point out that this function above is equivalent to this function below. So don't get tripped up by the fact that f of n minus 1 plus f of n minus 2 is on the same line. The fact that that's in one line of code is totally irrelevant. So I could just say value 1 is f of n minus 1, value 2 is f of n minus 2, and then I'm just adding those things together, and that's a completely the same function, just written a bit differently. But maybe it's more clear in the second case what happens first, that this is actually happening first, that you're stepping into this function before you even look at f of n minus 2. Okay, so I have some stuff here that I drew on the whiteboard last year and took pictures of, which can more or less serve as notes for this. But we don't need to go through it in super detail right now. I just want to have these in the notes for you. Just showing you step by step how the function calling is working. Okay. Yeah, so that's something that's there for you to look through. One question here is, what is the time complexity of this? So, and Tom actually asked this, I think, on the first day, is like, what does a 2 to the n time complexity look like? And now we're finally getting there. So that recursive function that called itself twice, the time complexity is not exactly 2 to the n, but it's close enough. Because basically, what's happening is that it's a tree, and that, so if I have f of 10, it's calling f of 9 and f of 8. And this is calling 2 functions, and this is calling 2 functions. And so the number of functions I'm doing at the bottom is pretty much 2 to the power of n, where n is how far down I have to go, because it's like 1 here, 2 here, 4 there, 8 there. And so now we start getting those 2 to the power of n functions, which again are usually bad. Like as I was saying on the first day, 2 to the power of n is not a very happy time complexity to have, but sometimes we need this behavior, and recursion allows us to do it in a way that I don't even want to think about doing without recursion. Okay. So question. So here's this binary search code I showed you 10, 15 minutes ago. So I just said that a function calls itself twice, like that one I just showed you. F calls itself twice, so it kind of had this 2 to the n time complexity. But I mean, this binary search is supposed to be really fast for searching stuff. It's supposed to be log n time complexity, but the function seems to call itself twice, just like we saw. So who can help resolve this contradiction? Penny?
It doesn't, because they're different if statements. So
Exactly.
in different cases.
Exactly. Binary search does not truly call itself twice in the way that our previous function did. There's an if statement here. So either it is actually only going to call itself once. Binary search is going to either take this branch of the if or that branch of the if. And in fact, it's going to take it with half the size of the data, which is where that log n comes from. So the point of saying that is you can't just eyeball the thing and immediately look at it and kind of pattern match in your head and say, oh, binary search, binary search, binary search, 2 to the n. Like, that's not quite right. You need to look a bit more carefully at what the function is actually doing. In this case, binary search calls itself once every time it is executed, just depending on which branch of the if. And if I scroll back up, sorry about this, gosh. If I scroll back up, this function calls itself twice every time it's executed. And so that's where we're getting that explosion of the number of function calls. Questions about this? Yes, Reiko.
Going back to the O log n thing, so the reason why it's O log
Okay, just let me scroll back there. I'll try to do it in a more painless way. Okay, yep.
So it's O of log n because you're going down one path of the tree, and then while you're doing that, the list that you're looking through gets shorter and shorter each time.
Exactly.
Okay.
So if the list is 1, 3, 7, 20, 50, I don't know. If the list is something like this, then the size of the original list is, what is this, 7 things. But then you're going to the middle element, and you're basically just throwing away half the list. So yeah, so every time you're calling itself on half, n here is really the length of the list. And so the length of the list is getting halved every time the function calls itself. So it's kind of like a function that calls itself with n divided by 2. That's also going to be log n, and which probably is something like that probably appears on your lab. Did that answer the question?
Yeah.
Any other questions? Okay, so the answer is exactly what Tani said, no, because of the if-else.